Hey, my name is Jason Zane, and this is my black hole lab project for Physics 2211 at Georgia Tech. In this lab, we will create a two-part simulation. For the first part, we will have a two-body system which consists of a star and a black hole. Using some fundamental physics principles and computation, we will be able to calculate the mass of the black hole. For part two, we have a four-body system which still consists of the star and black hole, but now we will be introducing a planet and a spaceship. Using the same physics principles and a new computational model, we will find an initial velocity for the spaceship that will allow it to not crash into the black hole. Before we get started, here's a quick preview of our results. For part one, we were able to calculate the mass of the black hole by averaging the mass of the black hole after each iteration, which this will give us the best estimate for the mass of the black hole. For part two, we were able to successfully find an initial velocity for the spaceship, which allowed the spaceship to not crash into the black hole. The fundamental physics principles we'll be primarily using in this lab are Newton's second law and Newton's law of universal gravitation. Using Newton's second law, we can derive the following formulas for momentum, the momentum principle, centripetal force, and we also know that in circular motion, the net force is always equal to the perpendicular component of net force plus the parallel component of net force. As always, we will have our position and velocity update formulas in order to calculate each iteration within our computational model. The assumptions we will be making for the first part of this lab include the following. Our environment consists of only the star and the black hole in the vacuum. In other words, there are no outside forces. Our time step is 1 Earth day, which is also equal to 86,400 seconds. Our system is the star only. These are our initial conditions. Mass of the star is 2 times 10 to the 30th power kilograms. Our observation starts at time t equals 0 seconds, and the mass of the black hole is currently unknown, but we will be able to find this in a bit. This is the mass of the star, which is given to us. And here we've calculated our time step, delta t, which is 86,400 seconds and is equal to 1 Earth day. Knowing the mass and velocity of the star allows us to calculate the star's initial and final momentum. With the initial and final momentum, we can use the momentum principle to calculate the star's net force. Here we are simply calculating the perpendicular and parallel components of the net force. Lastly, for part one, we will use Newton's law of universal gravitation to calculate the mass of the black hole for each iteration. After running the glow strip program, we are able to get the mass of the black hole over 465 iterations. Finding the average of these values will give us our best guess for the actual mass of the black hole, which in this case was about 2.17 times 10 to the 34th power. Here are the assumptions for part two. Our system consists of the spaceship, however the planet will continue to orbit around the black hole and our spaceship will be subjected to the gravitational forces of both the planet and the black hole. Our surroundings are the planet and the black hole. Our time step is now only 1 second, and we will launch the spaceship from the side of the planet that's in the same direction as the planet's motion. The initial conditions for part two are the following. The mass of the black hole is still 2.17 times 10 to the 30th power kilogram, which we found in part one. The mass of the planet is 9 times 10 to the 28th power, which is given. The units are kilograms again. And the initial velocity of the spaceship is unknown for now. We will now use the mass of the black hole we got from part one and use it for part two inside the glow script. In order to find the initial velocity required to escape the black hole's gravitational force, we will use the guess and check method. I found that an x velocity of negative 50 million meters per second and y velocity of 3 million meters per second was enough for the spaceship to not crash into the black hole. For the loop, we must utilize Newton's law of universal gravitation to calculate the net force on the planet and the ship. Next, we will use the velocity and position update formulas to simulate the motion of the planet and spaceship at each time step. This is the result for our glow script code. The cyan circle represents the planet's orbit, whereas the purple line represents the ship's trajectory with the initial velocity we found. We see that the ship was able to successfully escape the black hole. What does it mean for part one? How are net force and its parallel and perpendicular components different from the rate of change of momentum and its parallel and perpendicular components? Both of these formulas allow us to calculate the net force of an object and are mathematically the same. However, it is often easier for us to calculate the net force by finding its change in momentum since we only need to know its mass and velocity. That is, v initial and v final. It's usually harder for us to find all the different components of the net force and then add them together. What if for part two? What initial velocity would our spaceship need to have in order to enter some kind of orbit around the black hole? To answer this, I once again used the guess and check method. In this case, I found an x velocity of 0 and a y velocity of 12.4 million meters per second would allow our spaceship to enter orbit around the black hole. Here is the result of the glow strip code. Once again, the cyan circle represents the planet's orbit, whereas the purple circle represents our spaceship's trajectory, and in this case, it's also orbiting the black hole. Some potential errors are the following. Since we are estimating the black hole's mass using the average mass found after each iteration, this means that letting the program run for longer, thereby providing us with more data points, would allow us to get a more accurate estimate for the mass of the black hole. Our time step might be too large. A time step of t as t approaches 0 would give us the most accurate result. Since we are using the guess and check method for the spaceship's initial velocity, there are bound to be some human errors. Thank you.